Welcome! In this exercise, we have to show that the limit as x approaches 0 of sine x over x is equal to 1. Let's start by proving that when x is between 0 and pi over 2, then sine x is always less than x, which is always less than tangent of x. In order to prove this, let's consider the circumference of unitary radius. Let's draw a line through the origin, and let's identify by x the angle between the line and the axis. We will call B the intersection of the line with the circumference. Moreover, let's draw the tangent to the circumference, and let's call C the intersection of this tangent with the line. We will call A1 the area of the triangle OAC that we have obtained in this way. Moreover, we will call A2 the area of the circular sector OAB. Clearly, the value of the area A2 is less than the value of the area A1, since the circular sector is included in the triangle. Let's draw the line through AB. By doing this, we obtain a new triangle, OAB, and we call A3 the area of this triangle. Similarly to the previous case, the value of A3 is less than the value of A2, since the triangle is included in the circular sector. Let's now calculate the value of these three areas. The area A1 is the area of the triangle OAB. You should notice that this is a right triangle, since the segment AC is tangent to the circumference. Moreover, by definition, the length of the base of this triangle is 1. From this, we can immediately say that the hypotenuse of the triangle, this is OC, the length of the hypotenuse is 1 over cosine of the angle x. Then, the length of the segment AC will be equal to the length of the hypotenuse, 1 over cosine of x, that multiplies the sine of the angle, sine x. And this equals to the tangent of x. Finally, the area A1 is equal to the base 1 times the height of the triangle, the segment AC, which is tangent of x, divided by 2. Let's turn to the calculation of A2. The area A2 of the circular sector, OAB, is obtained by using a simple proportion. In fact, the area A2 is to the central angle x as the area of the circle, which is pi times the radius square. This means pi, is to 2 pi. By cross-multiplying the factors of this proportion, we obtain that 2 pi a2 equals pi x. This means that a2 equals x over 2. Finally, we have to calculate the area A3. The area A3 is the area of the triangle OAB. Notice that by definition, the length of the base of this triangle is 1. Moreover, if we call h the height of this triangle, we get that, again by definition, the height is nothing else than the sine of x. Then, the area A3 is equal to the base, 1, times the height, sine x, over 2. Since we have seen that these three areas satisfy this inequality, we obtain that by substituting the numerical values, sine x is less than x is less than tangent x. And this is exactly what we needed to prove. You should notice that this inequality implies that 1 over x is less than 1 over sine x. Moreover, this inequality implies that 1 over x is greater than 1 over tangent of x, which is equal to cosine of x over sine of x. Summarizing, 1 over x will be greater than cosine of x over sine x and will be less than 1 over sine x. Since when x belongs to the interval 0 pi over 2, the sine of x is always positive, as you may remember. Then we can multiply these inequalities by sine x, obtaining cosine x less than sine x over x less than 1. This is valid for every x in the interval between 0 and pi over 2. Notice that if we define y as minus x, then the condition x belonging to the interval between 0 and pi over 2 implies that y belongs to the interval between minus pi over 2 and 0. Moreover, notice that cosine of minus x is equal to cosine x. Similarly, sine of minus x over minus x is equal to minus sine of x over minus x, which is sine x over x. This means that for every x belonging to 0 pi over 2, cosine of minus x will be less than sine of minus x over minus x less than 1. In other words, cosine of y will be less than sine y over y less than 1, and y will be in minus pi over 2, 0. Overall, we have obtained that cosine x will be less than sine x over x will be less than 1 for every x in the interval between minus pi over 2 and pi over 2, with the only exception of x different from 0. Starting from these inequalities, let's define the functions f of x as sine x over x, the function g of x as cosine x, and the function h of x equal 1. Let's recall the squeeze theorem. Given three functions f, g, and h defined at least in a neighborhood v of x0, we assume in addition that the three functions satisfy these inequalities for every x in v, and moreover we assume that the limit as x approaches x0 of g of x is equal to the limit as x approaches x0 of h of x, and we call this limit L. If all these hypotheses are satisfied, then we can infer that the limit as x approaches x0 of f of x is also equal to L. In our case, notice that the limit as x approaches 0 of g of x is equal to 1, while the limit as x approaches 0 of h of x is also equal to 1. By applying the squeeze theorem, then, we can infer that the limit as x approaches 0 of f of x, which is sine x over x, then is also equal to 1. And this completes the proof and the exercise.